All right, so good afternoon, everyone. There's a lot about ChatGPT everywhere on the news, in discussions within organizations, within universities, within high schools, parent meetings, and etc. So here we take a slightly different approach. We're not doing it from a user perspective. We're trying to do it from a technology perspective. We look inside what's going on in GPT and ChatGPT in particular, and also the related technologies. So more general in generative AI. So we have multimodalities, images, how to generate images from text, and how to generate text from images. So we've lined up a group of very capable, enthusiastic ECRs, really career researchers and young researchers. So they're working in natural language processing, they're working in image captioning, explainable AI, adversarial attacks. So the schedule is slightly changed from here. So we have Suri Lee talking about the journey of GPT, OpenAI, ChatGPT or GPT models. So with that introduction into ChatGPT, Karen will give us a good insight of transformers and GPT and ChatGPT. After that, Naveed will look into how to fool deep learning and how to do adversarial attacks so you could have explainable AI. So you attack to explain. So that's exciting to hear. And Naya will do the multimodality, taking us to a journey of how to change images into text or learn images or do image captioning and how to generate images from text. And then, very interestingly, Professor Jack Amon, he has tried out GPT already. He's fine-tuned some GPT-3 on several textbooks, engineering textbooks, and trying to build a tutorial bot, trying to integrate into Microsoft Teams. And he's going to join us at around latest by 3:30. That's what he promised. Earlier will be 3 o'clock, so Zach will join us to take us on a journey on how to make use of it in teaching. Okay, so without further ado, I'll hand this over to Suri. So every time I call her name, it triggers my Suri. But the proper name is Suri. She's a postdoc fellow, brand new for the ITTC Center, working on Theme 1 and Theme 2 research on machine learning and NLP.
Thanks, Wei, to correctly pronounce my name. It's very hard to know my name correctly in Australia. So my name is Suri Lee. The talk today is called A Journey of OpenAI GPT Models. I'm going to start my presentation with an introduction to language model, timeline of recent language models, and then introduce the family of GPT models from 1 to 3. Finally, I'm going to summarize this presentation and give some thoughts about how I can combine GPT models with my research. So first, what is a language model? So basically, language model is a kind of machine learning models. They are trained on huge amount of documents or text tables, text. So after training, they have the ability to calculate the probability distribution over strings of text. For example, if we train an English language model and give 3 inputs, it is a brown dog, it is dog a brown, and dog is brown it, then the language model is supposed to know the first sentence is more like a English sentence. So it can give a higher probability or higher score to the first sentence than the other two. Also, a trained language model have the ability to predict missing words. For example, given the sentence to be or not to be, that is blank question. A language model is supposed to know here the blank should be the instead of open to all other vocabularies. And nowadays, most language models are transformer-based. Transformer is a neural network proposed by Google in year 2017. It contains an encoder and a decoder. So the idea of transformer is to use the attention. So given a text, the transformer pays attention on different parts of text to learning the meaning and insights of it. Later, after 1 year, OpenAI released GPT-1. The idea of GPT-1 is to use the decoder of transformer. So it's a unidirectional model. And train this decoder-based model on some book datasets to then got a pre-trained language model. Then fine-tuning this pre-trained model supervised NLP tasks like question answering, classification, or similarity. After 4 months, Google released the BERT. BERT compared to GPT-1, BERT used the encoder of transformer. So it's a bidirectional module. And in BERT, it increased the size of the model. So it has more parameters than GPT-1 and also have a large training data size than GPT-1. And in their results, they find the BERT have much better results than GPT-1 on fine-tuning NLP tasks. So maybe later inspired by the idea of increasing the training data size and the model size, OpenAI released GPT-2 in year 2019. So same, GPT-2 also used the decoder of transformer, but they've increased the number of parameters and increased the size of the training data size. In their results, they find if the parameters of the model can be increasing, so maybe the performance of the language model can also be improved. So later they keep this idea and implement GPT-3. So if we compare GPT-3 with GPT-2, we can find that the major difference is GPT-3 had 100 times more parameters and larger data size than GPT-2. And finally, this time, GPT-3 have quite impressive results on language modeling. Especially, it can generate some news, even for humans, it's very hard to tell if it's true news or fake news. Later, based on GPT-3, OpenAI constructed InstructGPT. So InstructGPT involves some human labors. These human labors to tell GPT-3 what questions are illegal or harmful you should avoid to answer, and what kind of answers are toxic you shouldn't give it to user. Then ChatGPT, which gains a lot of attention recently, it's a symbolic model of InstructGPT. So after comparing the blog between InstructGPT and ChatGPT, the major difference is InstructGPT used a model, the GPT-3 model. However, ChatGPT used GPT 3.5. But there's no official document or published paper to say what's the difference between GPT 3.5 and GPT-3. So in this presentation, I'm only go through GPT 1 to 3. And also, OpenAI say they're gonna release GPT-4 in the following months, which have more features and are more powerful. The title of GPT-1 paper is called Improving Language Understanding by Generative Pre-training. So the keyword here is generative pre-training. This is also where GPT's name comes from. In this paper, they find previous NLP tasks. They are mostly supervised learning methods, which means if we want to train a question answering model, we have to collect some labeled QA data sets to tell the model here is a question, here is the answer, and here is a document where you can find the answer. Also, if we want to train a classification model, we have to have the label data to tell the model here is input text, and here is the expected label. But the problem is sometimes it's really hard to get huge amount of label training data sets in some domains. Also, these models are independent, so it's very hard to reuse them into different tasks, even though these two models share very similar structures, but we have to retrain them from the scratch. So to avoid the issues in the supervised learning, GPT-1 have two phases. First, it's train a pre-trained model, also called unsupervised language model, like some documents, a huge amount of text. It extract the decoder of transformer and repeat this like for 12 times and link with a input layer and output layer. The objective of the pre-trained model is to maximum the likelihood of this equation. The equation here means given k words, the pre-trained model should be able to predict what is the next one. And the size of the k is decided by the context window. Later, they've GPT-1 fine-tuning this pre-trained model on some supervised data size. Like for example, for classification, it's fine-tuning this pre-trained model on classification data size. For multiple choice, it's fine-tuning this transformer on labeled multi-choice data size to update the parameters for different LP tasks. To get the pre-trained language model, they use a data size called books corpus, which contains 7,000 unpublished books. And also in their results, they find GPT-1 outperforms other state-of-the-art models in 9 out of 12 tasks. And there's an interesting finding in GPT-1 is they find if they delete the supervised part, that is, they only train a pre-trained model and directly uses on different tasks like classification, similarity, multi-choice, what's the results? And they find if we can increase the number of parameters or the size of the models, the performance of the zero-shot learning is keep increasing. So the idea is like if we can increase the size, the model size and the training data size, maybe we can get a more powerful language model. So this is the idea in paper GPT-2. The paper of GPT-2 called Language Models are Unsupervised Multitask Learners. So the keywords here are unsupervised and multitask learners. So unsupervised is easy to understand. They just delete the supervised fine-tuning part in the GPT-1 and directly use the model on different LP tasks like QA and classification. The reason is they find in GPT-1 there are two limitations. If in the fine-tuning part, we still need to collect different task-specific data sets. Also, we still need to retrain that pre-trained model on different tasks. So it somehow increased the difficulty of reusing the GPT-1. So in their solution, they want a more powerful language model. So they collect a larger training data size. Also, they replace the symbols into props. The symbols in GPT-1 is start, extract, and leap. They are the symbol to tell the model here is the start of the input, end of the input, and separate. Because it is in the supervised fine-tuning part, so somehow the model still can learn the meaning of these three symbols. But if now in GPT-2 we delete this part and only have the pre-trained model, so maybe the pre-trained model doesn't know the meaning of the three symbols, they never seen it in the training size. So that's why they replace these symbols into props. Here we can understand the prompts like a task description. Like for example, in translation, the prompts will be translate to French, and the input is an English text and a French text. The author gives two reasons about why this prompt can work. They say first, if the language model is powerful enough, they should have the ability to understand the meaning of the prompt. Also, they say because we increase the size of the training data, so maybe such prompts already in the training data, so the model already learned. For example, in this image, it's from their training data size. Between the English and French, there's already some prompt sentence like translated to English. So the model already learned the meaning of the prompt. So this time they use a larger data size called web text, containing over 8 million documents. So compared to GPT-1, GPT-1 only use like 7,000 unpublished books, so it's quite large. And in their results, they find GPT-2 achieved good results on some LLP tasks in 0 shot. For example, in the reading comprehension, here this point is the result of GPT-2. GPT-2 can somehow achieve SOTA results, or the gap is not that huge. However, in QA, question answering, the results of GPT-2 is much lower than SOTA. But if the author say if we separately looking at these four figures, we can find if we increase the model from number of parameters from 170 millions to 1,542 millions, the performance is also increasing. So in GPT-3 they they think about how about we increase the model size and increase the training data size to have a more powerful language model. But in GPT-3, they are not keen on 0 shot learning. They also introduce few shot. So to get the more powerful models, this time they collect a much larger data size. It's a mix of 5 data size. And they have 3 settings in the testing. It's called 0 shot setting, 1 shot setting, and a few shot setting. 1 shot setting means except for the task description, it also gives the examples to tell the model how to translate English to French, and then tell the model now it's your turn to translate cheese into French. And then in the few shot learning, after tell the model what to do, they gave few examples. Here give 3 examples, so the model can learn the pattern or the knowledge from more examples, then translate. And in the results, they find few shot, the performance of few shot is better than 1 shot, and 1 shot is better than 0 shot, which means their language model can not only understand the task description, also can learn the knowledge from the examples. And summary and the thoughts. So far, GPT models demonstrate the focus from GPT-1 to GPT-3 changed from like supervised fine tuning to unsupervised learning. And they demonstrate that the abilities of large language models for NLP applications. Also, so far, the GPT series of models is one of the largest and the most advanced language models to date, which we can see from ChatGPT is very quite powerful. But in the same time, we need to think about the cost of training such powerful models. Here, this full charts can give us a straightforward comparison about their parameters. So in GPT-3, it used 175 billion parameters, which is very hard for other institutions or organizations to copy their model and retrain it. Even though GPT models have achieved good performance on language generation, but they're still not perfect. They still have some limitations. So first, they have bias. It's because language models are learned from online documents. So documents will have bias, like bias on like gender or nation or something. And the second limitation is when we play with ChatGPT, we may find some answers look so convincing. But if we look at detail, we can find they just try to make up the facts. Also, the third limitation is lack of control. We cannot know what GPT-3 gonna answer in given a question. And also, if some user ask very harmful or illegal questions, maybe GPT-3 will give a toxic answer. So that's why in ChatGPT, it involves some human labors to guide the answer. And the fourth limitation is GPT models are trained on general domain. So if we ask some really specific domain questions like mathematics, healthcare, they may not have the ability to answer it or give some wrong made up answers. So some thoughts about how I can use GPT models. My research area is about knowledge graph. So for knowledge graph, there are two main streams. First is how I can construct a knowledge graph. So because GPT models is a very powerful language model, so maybe can use this model to do relation extract or IC identification. Also for knowledge graph applications like question answering, maybe you can use GPT models to facilitate the embedding of questions on the knowledge graphs. And so far, the GPTs are pure language models, so they can only do like on text level. If we can like compare the GPT with images, maybe it can be applied on more of these like multimodal knowledge graphs. Thank you.
Keep the discussions at the end. So let's welcome Karen to give us a more in-depth look at transformers. Karen, you introduce yourself.
Oh, yes,
Yeah.
sure. Yes. Yeah. Is that okay?
Yes.
Yeah. Sorry. Oh, yeah. I was looking for the mic. Okay. I just want to like walk around a bit, so if you don't mind, I just make it with the camera like this. Uh, Hello, my name is Karen. I'm actually a senior lecturer at EWA and currently co-leading the Australia Deep Learning NLP group. So I just don't want to have to go through the whole thing because I just want to say that I'm not like PhD student. Normally, when I just teach my unit, everybody just say that why this PhD student girl are just standing there, and I'm not a PhD student girl. Just want to let you know. I've been actually working on the NLP conferences and working with like currently with Microsoft and Google and NASA and US Air Force Navy and also the Australian Navy as well. I actually want to talk about this one. It's quite similar to what we actually do here. So firstly, in order to make this slide, I actually was in the discussion forum, the NLP community forum, which is organized by the Stanford and MIT and Edinburgh University people. I went there and I just want to talk about why this is actually really working and also what kind of feature plan that we can actually think of as well as this how does it really work. I think that as a computer scientist we need to know that not like ChatGPT is like a magic, and I mean we're not really saying like that way. We need to see like some people out of this computer science may just ask you why this is actually really working, then you may just explain that, oh, this is why. So I need to actually just give us some reason why this is actually really working. So thirdly, it's really golden age, thanks to Microsoft and Google. We just found that previously we haven't actually received a lot of attention like this. Like computer vision people always got the attention, but us, it's like, oh, you can just use like human language. That's all, isn't it? So thanks to ChatGPT, we finally got attention. So everybody just say that, oh my God, like, look, how cool is this? Like talking about this again and again, and then, Karen, can you just make the ChatGPT like that? Actually, I just want to talk about how this really working first, and how this actually comes out really good answer as well. As you can see that those both one is the result that I just asked, like what are the top tier conferences in NLP, and like how do I just really copy and paste the question that I used in Introduction to Programming Unit. So it's actually really working well if that is just a really general thing. So majority of these outperformed human performance faster than ever. Since 2018, the deep learning NLP like improved a bit. You can see that from 2018, if the human performance is 0 like that, is actually over the human performance. Means it's better than the human guess now. So as you can see, the handwriting recognition or reading comprehension, speech recognition, image recognition, language understanding, those are the things that human even actually confuse, but machine can actually do better than that. That's what we've actually found so far in the deep learning NLP area. So NLU is natural language understanding, and NLG is natural language generation. The reason why it's actually really working well is, I want to say that it's because of the model size and the parameter counts. So since 2018, as you can see that the number of model, the model size and the number of parameter counts actually increased by 10 times every year. So which makes sense, but we just actually want to talk about what is the pros and cons here. So, and it was last week, the Christopher Potts from Stanford University actually asked, do you have more than $50 million? Then, and you want to contribute NLP or deep learning. In that case, please make your new language model like GPT-3. Otherwise, it's not going to be working. So in our case, we don't really have that much money or $100 million or something. So we cannot really easily just generate this language model, like this large language model I'm talking about. Then what kind of thing that we can do? Before we actually talk about this one, how does a really big model actually work? So as everybody know that if you do the machine learning before, you know that like standard supervised learning, for example, polarity classification, like positive or negative, how can we do? Normally, we just try to create a data, positive, negative sample. As you can see that the left column just shows this text, and the right column, we need to have this annotation. So whenever we just like other people, client just ask us, I want to make this fancy prediction classification model, we just always say that, oh, we need this annotated data. Otherwise, it's not going to be working well. And based on that, this data, we just trying to train a custom build model to make a binary distribution. So that's what we normally do. What if we just try to do the similar thing? Oh, it's actually cut out a bit. But what if we want to have a different but similar problem? Let's say I like emotion detection or abusive language detection. It's actually quite similar to polarity classification, though we cannot really use this trained model directly. So that's why we need to relabel the whole thing, like angry, happy, like this different types of emotion again, and try to train it. So that's a standard supervised learning previously. But now we want to say that the language model actually works well with the feature learning. So feature learning, 0-shot, 1-shot, like Siri said, use large language model. Means to perform these previous unseen tasks. So even though you actually didn't actually teach this that much annotated data, you can even actually try it. So when I say that 1-shot, let's say, which is the example of positive feeling. Let's say Everybody know Willy Wonka, right? So I put the Willy Wonka here. So good morning, sunshine, Thursday, hello. And you can see that it's like positive feeling coming out, of course. Like some people are not in that Willy Wonka shoe. Obviously, they will not think like this positive feeling though. But it's positive feeling, let's say. Then based on this one, only this one, machine just trying to understand it, but based on past pattern, they try to have some kind of idea of how the human language is working. And then if the example is just coming out like that, they're just trying to find the similar cases about this one. So basically, with this one shot, is actually working well. Like negative feeling, just like no, like there's one example. So zero shot is really none of the example. One is one at least, and few shot is 10 to 100. So they just trying to put this one. And when it actually comes out visual learning, I mean, some of my previous students actually have been working on this area before, but everybody in the deep learning, even deep learning NLP researchers think like, oh, visual learning, maybe it's just going to be working well in the image domain, computer vision, but it's going to be very difficult for the NLP because the word doesn't really work like that. If I just see this picture, for example, computer, you will actually see that that's computer. But if I say apple, A-P-P-L-E, the word, some people think like the fruit, or some people think like Apple Mac, or MacBook, or in fact like laptop. So different types of imagination and then meaning actually comes out in one word. So it's going to be very difficult to explain it with the visual learning that we actually thought. But since 175 billion parameter, as you can see, that is actually almost similar to the current SOTA state-of-art performance. One of my students actually done this, and it's a little bit slightly higher than this, but please make sure that this is 0 shot, 1 shot, or D shot. So only 10 to 100 samples, they just achieve like this way. So then I want to say that it's not really because the magic. It's not because computer is small. I'm really sorry to disappoint you whole thing. It's not really about the magic. How does it really actually work? It's because of the transformer. I'm very pity to for Google now because Google actually made the whole components, but all the attention actually goes to Microsoft and OpenAI now. So firstly, the transformer here. So the language model that we actually want to say that if I just hello Australia, we try to think about like next word or context prediction. So that's what we do the language model, like next word. I can actually teach more detail if you come, and there's something down there. We have the CITS 4012 NLP course. So if you want to see like more detail, I cannot really explain the transformer in 30 minutes. So I just trying to make it more detail. So that's the language model, and they can do like dialogue system, like how are you, Karen? I'm good, thanks. This kind of respond can be predict, that kind of thing. So the encoder input to the encoder, and the decoder just trying to produce the output. And actually, the machine translation is the starting point of this transformer. And let's see how this encoder-decoder transformer actually works. And if you already know about this transformer, it's going to be boring, but I just try to talk about not just how does it work, what is the purpose is actually really working? What is the major point? Here, as you can see, that's encoder and decoder, and that thing is 6 of the encoders are stacked there. Not only this one encoder, just 6 of them is stacked, and the other 6 of decoder is stacked there. So they're just trying to put it, each of them. And the major point here I just want to talk about is multi-head attention and the feed forward. So the multi-head attention is number one thing in the transformer. The transformer paper name is attention is all you need. So I just want to just talk about briefly about this input and also the attention, why this GPT-3 can work well. First, we just trying to put the hello Australia as the input. Then when we just trying to put the input, we don't really just put this HELLO like that. Because if I put it like that, the transformer cannot really understand it. So the point is how to present the semantic information of each word. When I say hello, what does it mean? Of course, we can explain it, but when I explain it or when Wei explain it, it's gonna be totally different, right? But what is the way? The previous machine learning been actually working on specify each of the attribute manually, right? That's why we call this one a feature selection, manual feature selection. But rather than doing that, we don't know what kind of feature or aspects are important in order to represent these each word. We just trying to make a random 512 aspect. So means they try to make this one, the pink one is embedding, and the original transformer has this 512 aspect. So each of the square that each of them, there are 4 squares then, but actually it's 512 squares there that actually represent the hello meaning and the Australian meaning as well. So it's quite enormous that I actually don't know how to represent. So let's just try to make it like really large, random one. I don't know exactly what it is at the first time. And the position embedding is this transformer actually put this one not in like, as you can see the hello Australia. Let's say I have this I love you as a this order or you love me. The actual words are saying I and love and you, but if the order is changed, the meaning is totally changed, right? So that's why the order in the sequence order is very important. So that's why the position embedding, they're just trying to put it there. Which one is this first, second, third, like that. The simplest way they just do is there are really different types of position embedding they actually do, but the original transformer actually uses sine and cosine, combine them, and then trying to distinguish each of this first word, second word, third word, like etc. So if you see this x1 to x2, the gap between them is actually smaller than x1 to x10, like that. So they just trying to understand that the gap between this position. So using this embedding, the random big aspect embedding and then position embedding, they try to use this together and then make this text position embedding. And that's this input of this in encoder. So then after we have this one, you can see that number one key point is how we represent the word in enormous amount of aspects. So if I explain about me, I'm not really using my own like sorry, I'm just Asian girl. I don't really say like this the actual thing, but I just put like 512 random aspect. We don't know exactly what it is, but it's just coming out like that large, huge one. The second one is, as I mentioned before, attention. So the multi-head attention, for example. So multi-head attention, as you can see, V, Q, K, Q, like that. And then you're just having these scaled up product attention. What is this exactly? So then we have each of these embeddings. Hello, Australia, I'm here. Then we have each of these X1 and multiply with this W weight matrix. As you can see, WV, WK, WQ. And then make this one query key value. Multiply each of them and then make this one. And maybe you just ask a question like why we have this query key and value. If you know how we just store the data normally in the computer, it's very easy. You can see that if I just try to compare a word here to something else. So here to hello, here to Australia, here to we're just trying to compare it. But what is the best way to compare two different words? And as you can see that in this way that we normally store the data is key and value, right? So that's why they normally have this each of the word, hello, Australia, I am here. Each of them has the key and value there. Then it's like easy to compare with this here, hello, here, Australia, here, etc. So that's why query is the certain word, and that we want to compare with the actual index, which is the key and value there. So basically, it's working like this way. Each of them just put this one with weights, query key value, and then just get it at each of this query key value, like that, each of them. And after that, they put this one, query and key, multiply them. Why? Because we want to compare with two-word correlation. That's why we do query and key first, and then put this one to softmax. Why we put the softmax? Obviously, it's just trying to make this one score value. So that's why we have this one score, normalized score value, trying to get this softmax after that. And then after you have the softmax, which is here, this part. So you put it this one, the query key, the correlation, the score, which is from the softmax, and then trying to multiply with this V value again. Then you will get this attention score of this part only. But if you do this like again and again from hello, Australia, I and M, just compare with two words again and again and again, in enormous large size of the calculation, then you will get these Z1, Z2, Z3, Z4 like that, and try to make this one a matrix in the end. And then after you have this matrix, not so fast, it's not finished, we have this H. So this is why we call this one multi-head. As you can see here, this is H that actually has multi-head. Not just this one time, they just do multiple times. Let's say if I just put it like multi-head 8 times. So then 8 things will be concatenated, this Z matrix, concatenate this 8 of them. That's just the one multi-head attention. This is just one, but as I mentioned before, it actually has 6 of them. 6 of them, like it's really, really large. So the point is, BERT or other Google actually thought they actually used this one, really enormous one. But GPT, in this case, as I mentioned before, we're using like language model, means next word prediction. That's what they're actually doing. That's why we don't really need this whole thing. Because if I put this whole transformer architecture, that means we need to compute too many parameters. That's why we don't really need this or this, because this multi-head attention is from here as an input. That's why we don't really need it. So we have these 2 out of them, and then put this one to decoder only. But the decoder only, as you can see, that is a little bit different. It's masked multi-head attention. So you can see that other things here, and here is just multi-head attention, but this one is masked multi-head attention. Why? Because we need to understand that the next one. And so we don't have to really understand the whole thing. The calculation is same, but if let's say this we work in this Australia part, we need to try to find this next word, for example, after this Australia, then we need to hide this, right? I and M. So what we do is just multiply with minus something, really infinite word, infinite value. In GPT-2, they use this billion, minus billion. So that's why we're just trying to reduce the probability of this I and M, because we need to actually predict this next word. So they just do this query key and value like that, and then calculate these, and then get these Australia. And after these, Australia goes to next word, and then this starting hello Australia actually trying to get these I like this again and again. That's the decoder only block. So the GPT-1 just use this masked multi-head attention and feed forward. That's all. But it's not really working well. And Siri already actually mentioned this one. I'm not going to talk about this in more detail. And the GPT-2 now, this is a bit different. So as you can see that they put the layer norm prediction chain, and then after this full decoder, they have this layer norm again. It's just because they focus on the efficiency. The layer norm means they're just trying to reduce the vanishing gradient issue. So even that has really long document, they're just trying to reduce that and then make it the efficient one. So that's why this trying to put this layer norm like this, and then the residual connection just put it like this one again in order to reduce this vanishing gradient as well. So as you can see, all about that is same as transformer, but trying to make this efficient model. That's all, basically. So then let's see, GPT-3. What do they do? It's like really large data, web text. GPT-1 was just book crawl, and GPT-2 is like web text. And the parameter, obviously, because the layer was 12 at the first time, in this GPT-1, GPT-2 extra large model, as you can see, there's 48 decoder. It's not just one decoder, you just have 48 decoder. I mean, that's why this parameter is 0.5 billion. And the dimension, you remember the dimension is this number of aspects that you want to represent the word, for example. I mean, original transform actually used 512, but GPT-2 actually used this 1600. And that not so fast. GPT-3 has common crawl, which means not only the website contents, they're just trying to get this common knowledge and all these big bunch of sources, not just the website only. And then you can see that dimension-wise, it's 12K. In order to express, represent me, they put this K, 12K aspects and each of the word. And then you can just see that parameter, look at that, 175. And then they use the spot attention. The attention actually originally just calculates the correlation between two words again and again, but the spot attention is just randomly select them or the sliding select them or global attention. So just trying to reduce the attention calculation time. So that's how it really works. So why does this really work? You see the point now? The only objective is like to learn the co-occurrence pattern. So comparing every word in the sentence to every word in the sentence itself. So I can just briefly explain what it is. Increase the dimension. So increase the number of random aspects that represent each term. That's what they're doing. For example, we don't know what the best, smartest way to represent this word, but maybe I can just put big bunch of random aspects. So 768 at the first time? No. What about this 12K aspect? We're just trying to increase again and again. And the other one is increase the parameters and model size, just trying to have more data, more correlation, and more. So does it really work well, GPT-3? So if I just ask a really simple question, you have to work really, really well. This is the one I actually did that yesterday. GPT-3, not ChatGPT. So it's not really perfect when we actually ask about the reasoning question or checking the answer. So you can see that which one is heavier, toaster or pencil? Pencil, come out. The reason why they're doing this, they don't really understand the context. It's more like based on the pattern. And then how many eyes does my foot have? It's a bit creepy that they said it's like I have 6 eyes on my human feet. And like, who was the president of the United States in 1400? George Bush. He's not even actually born at that time. So those kind of the reasoning is not really possible in GPT-3. And then what's the solution? They've been actually thinking about this one after this GPT-2 and GPT-3 comes out. They also actually present their work as well. And then they just thinking about what is this solution? When the GPT-3 comes out and they just think about, what if we just do this? Human. It's always data human, the word is like this. Now, so Instruct GPT, January 22, they're just trying to put this human feedback. Of course, they just try to say, oh, we're not just using the human feedback, we're just having this reinforcement learning together. But actually, human feedback is enormous part. So, and then ChatGPT, same thing, but with the safety. So what I want to say is, this is Instruct GPT, which is the one, as I mentioned before, the RL with this reinforcement learning with these human feedback. So important thing are 2 points here. Labels. So they have this human label demonstrate that whether this is good answer or bad answer. At the first time, what they do is just make this binary. So you can see that binary is good answer or not. And then in the end, they actually put this reward to best to worst. They're just trying to make this order. That's what they're doing. So actually, you don't have to really disappoint this because, of course, there are human there. It's not really about all the machine actually did, but still that means that human effort is quite important and it's like we're not really useless anymore. So, which is good. And then I also find it like yesterday, OpenAI hiring the developers, more human developers to make the GPT better at coding. So they're just trying to find whether this is bad code or good code and how do they change the code, those kind of feedback. And then you can actually also apply if you want, that's expert AI teacher contract. is there, still there actually. So that's what they're doing. And also, not only these area, Microsoft and OpenAI are actually still hiring, and that's what actually one of the project that I'm actually doing with Microsoft. We're currently using this reinforcement learning with the human feedback for not just using the chat, but also using this multimodal image or video as a content. So the future work that NLP community discussed last week when I was in the meeting. First thing is human interpretable. Navi will actually talk about this one, like Sai later on, explain about yeah. But human interpretable and reasoning should be necessary. As you can see that the question here, how many letters are there in the word 19? And the answer is there are 9 letters in the word 19. Dot. So it's like 9 letters, characters. And no, there are 12 letters in the word. If I just say that as a user, then suddenly ChatGPT will say, you're correct. My answer was wrong. I apologize this. Yes, it's indeed 12 letters. 19. Actually, it just has like 8 or 9. But are you sure there are 12 letters? Really? Then if they ask it again, then I'm sure that there are 12 letters. Really? That's because ChatGPT doesn't really understand the point, but just trying to understand based on the pattern. And then when humans say something bad about them, they just, oh, maybe I'm wrong. Maybe I need to actually apologize it. That's what they're doing. If you just try to do that, just you can see the same thing. I mean, I did this like a few weeks ago as well. And the other one is also these days, who just really type it all the time in order to search this one? If you just try to get some kind of information or something, you normally just watch like video or image. As you can see, the App Store, download the TikTok, YouTube, Instagram. All the people these days just trying to get information from the YouTube or the video a lot. So rather than just watching that actually whole video, you may just try to put this one to chatbot and get these like summarization or do the question answering. That's what they're actually doing, and with these Microsoft and my team as well. Yeah, that's all. Yeah, thank you very much again.
Yeah.
Yes.
You said that the word was first interpreted by 512 boxes.
Yes.
Then it went to 12K.
So the word should be represented with random aspect, 512 aspects at the first time. Yes.
So these aspects
Yes.
come from, I guess, the web.
At the first time, they just put the random value, and then based on that, you can see the output, isn't it? They just trying to train it. Is random guess was correct? No. Update this random again.
And who decides what's good?
Yes, they have, at least they have 1 or 2 cases, yes. Because if you think about this language model, let's say if you put this whole book, you already know what is the next word, right? So that next word is already there in the book. So they're just trying to train it based on that. The train means they're just trying to say that after hello Australia, we expected I, let's say, in the book. But if I just put it like random word Canada, let's say, then they will say that no, it's not. Then they just trying to calculate the loss between this I and the Canada predicted one, and they're just trying to train this one again, the model here. And then now the random aspect value, it will be changed, updated.
If I'm trying to ask who or what decides which is the right or correct or the expected direction.
The actual book is already written, right? We know that what word should be next. Yes. Yes.
Loss function, and loss function is gradient descent. We have a back propagation to update the weight.
But you need to have the book written.
Exactly.
What happens if you don't have the book?
But we have a lot of books. That's why the GPT actually really works. If you don't have a book, that's the problem. I don't think that's working out well. Yes. Yes.
Because we collected lots of
Books.
data.
Yeah. Books or website or the data, any contextual data. Yeah.
Even the previous one.
Yes. I mean, I want to say that machine originally just really mimic what human actually did before. So that's why, oh, this is what human actually written before. They're just trying to mimic. That's the starting point. Yes. Oh, yes, yes.
So thank you for that. Look, I've been playing with this, and I've found a significant weakness is in providing references to information.
Yes.
So I've done a couple of test things, and I've said, write me an answer about this and provide references.
Yes.
50% of the references are made up.
Exactly. Yeah.
Is that deliberate? Because I think it. Well, I'll let you answer because the authors are right.
Yeah.
They've worked in the field. The book or the journal article sounds about right, but it just doesn't exist.
Exactly.
Is that deliberate? Is that a way that they've put in there to try and safeguard cheating in some way?
But actually, that's why we have these human feedback. Current with
But it's made up.
Yeah, it is made
It's
up.
not that it's not correct. It's actually, it's not that it's the wrong word. It's actually made up. So it's more than just, I can't correct it because it's fake.
Yes, actually, that made up is also from the previous contents. They trying to use like merge different types of words and then trying to base the pattern they just made up. So when we say that made up, it's not really critically made up. It's just really based on the previous reference. Or maybe I can just make up like putting like this one, that one, like that, and then just put it that result based on that. So apparently that kind of thing should be cleared to reduce the problem by using the human feedback. You should not make up like this way or that way. We need to actually give us like different types of examples. Which one is really made up pattern? Yes, but very good question. Thank you. Yeah.
Could be like confidence factor. Sometimes, you could say your answer is correct to 80%, and if it's below a threshold, you can say, I don't know. Because same thing, you ask something, you get some.
Yes, so previously we have this confidence value actually, but if we do that, then actually computation time is actually really long. That's why in the end, they just using this human feedback later on, and then trying to order the actual good answer to bad answer ordering. So if you do this for multiple times, they just trying to learn this pattern again, statistical pattern again. Yes, yes, Chris.
Like I thinking actually more of it as a search engine. In a search engine, it's going to remember the relationships between the items that it looks at. It's also going to tag the relationships with where it got your data from. So that's why in search engine it's able to list the author and the title and the subset. But here, everything is thrown away, regardless of where it came from. It's the contents of the words. Put in the vectors and numbers, which really mean no sense. You can't reverse the vector to go back to where it came from. So I understand your question because it confused me as well. Why does it make these things up? It's not consciously making it up. It's just doing what it always does, but it comes out as rubbish.
Yeah, actually, Chris is exactly right. So there is no pattern or the reasoning at all. So there's no reason they actually do that. They just got this, because this is the pattern that we just have from the random aspect. That's why they're just trying to get this pattern. But if you just try to reverse back, which is wrong, you need to go back. You cannot really make it like that because there is no hierarchical reasoning process here.
So is there any logic in my understanding of this? Like it's trying to write a sentence and knows how to start it, but then just makes up the end of the sentence so it kind of makes sense.
Yes.
And that's how it came up with false references.
Yes,
because
exactly.
it kind of makes sense.
Yeah, I think you might be right because you look at some of them and go, well, I recognize those authors and the book kind of sounds like it could exist. But or the journal exists, the authors exist, but they're going to publish that journal certainly under that paper doesn't exist.
Just
but they'll publish it in the future.
But one more thing I want to say, you actually trying to thinking about like that way, but machine never think like that logical reason. So if you just keep asking about why this coming out, I don't know. You just give me that kind of data set before, and then you have this random aspect like this before. So that's why I just generate like this way, this kind of pattern. But we don't know why this is really working. So that's why the human feedback is important, because we cannot really change this logic because there's no logic there. So they just keep saying the binary good or bad answer again and again.
The probability of way is associated with you, and so way you will be predicted at the alternate. And then the journal name is tend to be probability based, and often those words together make up a journal. So your journal names and author names both legitimate, but then the combination of them may not be probabilistically evident. So that's why there's the association between author and journal name, and then the title of the publication.
Which may actually be a really useful way to detect cheating. Because if you put something through, turn it in, if the references are real, it should flag them as being used before. If the reference is made up, it should say, I've never seen this before.
Yeah.
Right?
We can say that, yeah, based on the memory, yes.
And therefore, if students submits a piece of work that's got references that turn it in as never seen before, that could be a flag to say, hang on.
Okay, so I'm conscious of time. Let's move on, and it's very useful discussion, and especially do this all the time as well. And this is the first technical discussion of ChatGPT. We could carry on this into discussion.
Just last question. So is it actually looking at everything that's on the web and all the knowledge we've got,
Yeah, we don't.
all the papers, all the books?
There's actually so if one thing as the person from law identified all sorts of issues on this change, technical issues and IP, copyright.
All patents, anything that's disclosed.
There are some, yes, yeah, but
Okay, so our next speaker is one of our very distinguished DACRA award and different grants and awards. So let's give David the stage to tell us about explainable AI.
Hi, everyone. I'm Naveed Akhtar from the Department of Computer Science. I'm a senior lecturer there, and I am currently also an Office of National Intelligence Research Fellow. The title of my talk is Pooling Deep Learning in Computer Vision and Addressing It with XAI. Now, since the title does not say anything about ChatGPT, so I must tell you how this is related. So, as you know, ChatGPT is basically a product of natural language processing domain. And this domain is exploiting a technology called deep learning. And in a sister domain of computer vision, which is my field, so we are also basically using these deep learning technology very heavily. And basically the principles of the techniques that we are using in computer vision, they are basically the same as natural language processing because of this deep learning. So this is how it is related. And the other thing that I wanted to mention is that this presentation is based on what projects we have done at UWA. So at times you may feel that I'm going a little bit more specific, so the content is more specific than generic, but I have tried to make it as general as possible for everyone's understanding. Now, if you have ever sit with computer vision people, they are always talking about deep learning because deep learning is actually doing great in computer vision. This is this is an illustration of a deep learning model, which is a visual classifier. Basically, if you give this classifier any image, it has kind of human level capacity to predict its label correctly with high confidence. Now, but at the same time, this model is a black box. So we cannot really explain in a human understandable manner that what this model has learned from its training data and how is it using it in making its predictions. So this is true in general for deep learning. So the NLP domain or field is also facing this problem. So yeah, now since I've just said that this is a very pervasive problem, the black box nature of deep learning. So I would like to explain it further. What does it mean to be a black box approach within machine learning context? Now, this model that you are looking at here, it's basically a set of layers, a stack of layers. Each layer, you can imagine it as a function, so which is taking input from the previous layer and producing some output, which is further processed by the later layers, which means that this function, the overall model actually represents a hierarchical function that has where each function has its own parameters. Now, when I say that deep learning is black box, it doesn't mean that we don't have access to these parameters here. We actually do have access, and to an extent, if we locally look at these parameters, we can also kind of explain to a certain extent that what these parameters are representing. But the problem occurs when we are looking at the holistic model. So the model as a mapping from input to output. Then since there are a lot of parameters involved and there is a very heavy interaction between these parameters to make the prediction, so it becomes impossible for us to explain in a human understandable manner that what's really going on inside the model. The upside here is that since this overall function is quite complex, so we can do some amazing things with this. So very complex tasks like predicting the label of an image at a human level accuracy. But at the same time, it also makes deep learning a breeding ground for adversarial attacks on artificial intelligence. So basically, it is very easy for us, since we don't really know what's happening inside the model, it becomes easy to manipulate the model and exploit this complexity of the model itself. For example, in this case, this is an actual input that I'm showing here, for which the actual output by the same model is an ostrich. A moment ago, it was correctly predicting it's a dog. And in this case, the prediction is a flower. Now, what's happening here? In the first case, what I'm doing here is that in this image, I am adding a very light, very low power signal, which we call adversarial noise or adversarial perturbation, to get this particular image. Now, for us humans, these two images are almost the same. So the perturbation is imperceptible, but for the model, it becomes something like this. It's an ostrich. Now, in the second case, you might have guessed, so this particular pattern of a star, this is what is causing the problem. So this is what I have done here is that I have made the deep learning model sensitive to this particular pattern here, such that it will always predict that this is, any image that has this pattern, it will say it's flowers. Now, this kind of change from puppy to flower, people don't really mind, but sometimes things can get serious. So we had a couple of projects running with DARPA on this particular problem of adversarial attacks. So this kind of manipulation, we call it simply adversarial attacks. So we had a couple of projects running with DARPA in collaboration with University of Central Florida. And these projects were basically, there was a work that we did at UWA. So that was the precursor to these projects. And this is basically the framework. I will not go into the details, but just give you just talk about the key finding. So basically, the key idea here is that although deep learning models are susceptible to these kind of adversarial manipulation, we can find some solution. And in this case, we are finding it in terms of learning a neural model, which is kind of layers that we can append at the start of this visual model here. And this model can actually take the adversarial effects of the perturbations out of the input. So we can actually clean the input with this kind of approach. So this worked well, but within in the DARPA projects, we actually we found out that basically, if you make this kind of model public, like assuming that your model, your classifier here is it's public knowledge, which can be exploited. And if you also make this denoising model here also public, then this does not really work. So you have to keep this particular model secretive, like a secret key in networking. So just to give you an example, that how this works in actual. So this row here, it is showing some original images. So they have been predicted correctly with these different models. As you can see, the confidence rates are quite high here. And these are the perturbed images, the attacked images. So you can see some perturbation here, maybe because we are using high power noise here. And in all of these cases, so this particular image, this becomes a wooden spoon for the model. This is a pencil box, and this is a green snake. And we have high confidence on all of these predictions. Now, with our approach, we were able to rectify these images such that we were able to restore not only the label, but also the confidence scores of these images. Now, in this kind of approach that I have just discussed, what is happening here is that I'm manipulating the images. So the model by itself, it remains clean. But in the second case, I had said that I'm making the model sensitive to a particular pattern here. So which means that the model has to be corrupted. In the second major project that I was involved in, so this is related to my recent fellowship with Office of National Intelligence, what we are trying is that we are trying to address this. We are hoping that somehow explainable AI can be used to see if the model is really sensitive to these kind of irrelevant patterns. So now these kind of manipulation where I'm making the model sensitive to certain patterns, these are called Trojan attacks or backdoor attacks in computer vision. And this is an example of this attack in action. Basically, the attack behaves like this. If you give a clean image to the attacked model, which is a compromised model, it behaves normally. But if the same image or any image has this trigger pattern inside it, the model misbehaves. And this trigger pattern is something that is only known to the attacker. So this can be something like, in this case, a tattoo, or maybe some nameplate on the shirt of the person, or something in the background. So all of these could be used as a trigger pattern. So in that, you can imagine that this is kind of a very practical scenario here. But at the same time, I have just said that we need some access to the model. So we need to manipulate the model, which means, so normally it is thought that since the attacker needs to access the model and make change, so maybe this attack is not really that practical. But actually, you have already seen that deep learning technology by itself, it is resource intensive. So normally, for example, in ChatGPT, GPT-3 model, so there are 175 billion parameters. So you cannot really train these kind of models on local machine. Basically, not everyone has this kind of capabilities in terms of resources. So normally you have to uh, use some third-party resources. Sometimes you have to uh, get your data labeled through third parties. In that case, they can poison your data, and such that when you train the model, it will have a backdoor in it. Or maybe you can just basically get the training resources, GPUs of some third party, and they can inject a backdoor in the model during the training. Or simply, you can use some pre-trained model. For example, just use ChatGPT for some purpose, and there is an embedded Trojan in it, such that whenever it sees a particular pattern, it will be behaving in a particular way, which could be misguiding its user. So, as I mentioned, the main idea of this project that I'm currently involved with is that we want to use XAI to answer the question that can we handle this situation, this model manipulation with XAI. So the first thing, of course, is then to look at what is available in the vision domain in XAI. So it's actually kind of a little underwhelming. Basically, what is available is that we have tools currently that produce these kind of explanations where we give, basically we have an image, we give that to the model and we get the prediction. Then all this explanation tool is going to tell us that where the model was looking at in the image to get that prediction. So it's a heat map that is telling us that. In this case, it's a cat. So the cat is highlighted. In this case, it's a dog. So the dog is highlighted. Now it generally works, but sometimes the results are not so great. But it is kind of, people are happy with it at the moment, it seems. But yeah, and since XAI is kind of something that people are generally interested in, so I thought to also include a small one slide about an approach that is one of the most authentic techniques in XAI in vision domain. It is based on game theory, basically, so it has good theoretical foundations. So just to give you an idea how this approach works is, let's say that we have a model that we want to explain, basically with respect to this image. We want to see where the model is looking at when it is going to make this prediction about this image. So for this image, we will define a baseline image. That baseline image means an image that does not have any features of this image, the input image. And between these images, we will define a path, which is a simple linear path in this case. And on this path, we can compute images. So this is just, you can interpolate between these images to get these in between images. Now, then we give this baseline image to the model and use the gradients of the model with respect to this input image. Now, in XAI, in general, there are just two signals that people normally exploit, and both of them are based on the model. So first one is the forward activation signal, and the second one is the backward gradient signal that can be computed with backpropagation techniques. So this particular technique, it is completely relying on this backward signal. And what it does is that for each of these intermediate and the input and the baseline images, it computes these gradients and then combine them. So this is basically a very easy technique in that sense. And finally, what you get here is the activation map that you can show on the image as a heat map. Now, here at UWA, we have also contributed to in this field, in this direction of XAI, just following the existing paradigm. And if you are interested in knowing more about these XAI techniques in vision domain, there is an accessible short survey that I have uploaded basically just last month on this topic, so you can look at that. Now, looking at this literature, one thing was very clear that although we are talking about XAI here, but the approaches that we are looking at, they are not really helping us to look inside the model. For us, the model was black box before we had used this XAI approach, and it remained a black box even after we had used it, because all we know is that where the model is looking at in a particular image to make its prediction. So there is no generic information as such that is available to us. So in this case, we had to look to get to a tool that we wanted to use. We had to look further deeper into our previous research. And that again links back to the adversarial perturbations that I initially talked about. So you can recall from the previous slides that we had this example where this dog was becoming an ostrich. But in this case, this particular noise signal that we computed, that was specific to this image of the dog. Even if you change the pose of the dog in this image, this perturbation will not work. So here in our lab, we were also developing a kind of perturbation, a noise signal that would be able to work on any image of a particular class. For example, if you have a class of ostriches, you add this signal to it, all of these images will be understood as German Shepherds by the model. But if you add the same signal to other classes like jellyfish, it will have no effect. So this is a particular way of constraining the problem that we were dealing with in terms of generating this adversarial noise. And when we were doing it, we observed there that we had a certain level of correlation, some geometric patterns appearing in our perturbations, which were not there initially in this input specific noise. So, and interestingly, we were also using model gradients to compute these kind of noise. And later on, we discovered that these are the main ingredient of XAI as well. So these gradients are actually capturing some of the information inside the model, that what the model thinks about a particular concept, or at least partially thinks about that concept. So we then, we also verified this particular phenomena by using a classifier, which was a robust classifier, as a generator. So what we are doing here is that this seemingly random input, we are giving it to our model, and then we are computing a perturbation signal, saying that what is the perturbation that I need to add to this signal to make it like a hummingbird, to get it treated like a hummingbird. And when you add that perturbation to this signal, so you can see that already the pattern of hummingbird started to appear here. And we tried it with multiple inputs, and every time, so the target class was starting to appear in the input image. Now, I should mention here that this is a classifier that we are attacking with our attack. It's not a generator. So you can see that deep learning by itself, these models, they have an excellent capacity of being used as a generator. And similarly, we use some other, we input some other images, attack them to make them, to basically manipulate them. So in this case, we were able to create a primate. This is a turtle. So again, these are attacks on classifiers that are behaving as generators. Now, based on this observation, we actually developed a technique that that could provide us the tool to look inside the model. Basically, what we are doing here is that, as I had initially mentioned, that a model is basically a very complex function. So with this function, there is an associated loss function. So, and in this loss function, you can think of it like this, that if the model is able to recognize ostrich, all of these images of ostriches, they will fall into some local minima on this loss surface. So here I am just showing this with white circle here. What we did was that we assumed that we have certain data set that is available to us. This data set does not have to be the same data set that has been used in training the model. It can be any data set with images. So from this data set, we take some samples, we throw those on the loss surface and compute that what changes we need to make in those images such that they become, in this case, like ostriches. So we computed those directions, we integrated that information, then we basically iteratively kept on integrating this kind of information, and finally we refined that information to actually visualize what the model is thinking about a particular concept. So these are some of the results here that we got. So you can, here the concept means, so these are typical, sorry. So these are typical examples of images that have been used in the training data of the model to learn the concept of thimble. And you can see, if you look carefully, so these visualizations, we are able to reproduce the main features of thimble here, and they have been reproduced using model as a generator and with model gradients. So this was true for most of the cases. So we were able to successfully basically look into the model here, and these explanations, these are not input specific. So they are input agnostic explanations. And these are some results on another model, which are again reasonable. So what we now want to use this explanation tool is to see if we can find this sensitivity of the model with respect to the trigger patterns. So what we did was some experiment in which we chose a target class for a model. Basically, what's happening here is that whenever you put in this Nike sign in an image, the model will think of it as a castle. So this is with 100% probability. So we trained this model, so an Trojan embedded model, and then we tried to explain the concept of castle with our algorithm. And surely enough, we were able to see some signature of the trigger pattern by itself in our explanations. So this was something quite exciting for us. And this was also true for other patterns as well. Yeah, so basically this is the most recent work that has been, it has just been presented last week in AAAI. So this is all from my side. I just wanted to conclude with some of the things. So firstly, we know that deep learning is doing great in NLP and computer vision, but we need to be careful that this technology is a black box technology and it is highly susceptible to adversarial manipulation. And what our research has so far shown is that all of these domains of XAI, adversarial manipulation, and generative modeling, they actually converge to a point where they need to exploit the gradients of the model. So basically, all of these fields, problems, they can work together to finally make deep learning a little bit more trustworthy. So yeah, that's all from my side. Thank you. Okay. Questions?
Gonna talk to us about image captioning and text to image generation.
So, good afternoon, everyone. Can you hear me? I'm not really loud, so that won't be a problem. Thank you, Wei, for giving me this opportunity to talk about this interesting area. So, today I'll be talking about models that connect vision and natural language for interpretation and imagination. So, we're talking about generative AI. And for it, connecting different modalities is sort of essential. And so connecting vision and natural language, it plays a very crucial role towards the models that we want to see in future. So what do I mean by interpretation here? It's a broad term. Even detecting objects can be termed as interpretation. But what I'm trying to say here is interpreting visual input with natural language descriptions, right? So we as humans, we spend initial years of our lives developing this ability, and it gets better with time as we develop our language skills, as we get some common sense running. We see the magic happening. It's so natural to us that we don't even notice the processes that run behind this. So why are we interested in creating models that can do the same? Well, the first reason I can give you that it can revolutionize the way we do our task. Around 300 million people in this world, they are visually impaired, and this technology, it has the potential to enable them verbally see their environments, navigate independently. Apart from that, we are well aware that internet has this, visual and textual data that is growing at a fast pace. Yet our algorithms, or we have very little knowledge of what's there, and we would like to index it. And we won't like to index it just with, tags and stuff, but having some natural language descriptions associated with them will help more targeted queries. Apart from that, we are, in a habit of recording a lot of activities that we do. And then these algorithms can automatically create textual diaries, maybe suggest some, positive habits or, ways to improve our lives. And with robotics, if you want our robots to actually communicate with us and understand their surroundings, this is important that they make sense of things around them, and then if they're able to communicate these things. And quite recently, medical community is also getting interested in this. Why wait a week or a month to get a report if it can be there in just a matter of minutes, right? Again, accuracy is a major concern here, but then this is what, we hope for in future. Okay, so we know that this technology can be very useful. And so how the models that, enable this, what is the architecture, what is the pipeline? So from 2015 onwards, this task, it has been addressed with an encoder-decoder based pipeline. So I'm not going to go in the details, but give an example. For example, when we look at an image or, when we are somewhere, we're observing something, we kind of make a mental map or some mind map inside our brains. And now I don't know what that presentation is because it's very unique to your experiences. But based on that, you're kind of transforming visual information into language. And this is what these models, they try to mimic as well. So the encoder that you see here, which was initially a CNN and is being replaced by more, advanced models, it tries to extract the most meaningful information, the most useful information that a decoder can use to generate text. And with time, these pipelines have been augmented with more useful features such as semantic concepts, relationship between objects, the overall layout, to make the encoding more meaningful. And we have seen a lot of progress. So the encoder part, a lot of evolution happening from CNNs to now transformers, and whereas decoders started from RNNs, recurrent neural networks. And by the way, they created a lot of buzz. So Karen, NLP got attention when RNNs came, and that is why we saw a boom in captioning. And now we have transformers. So on paper, things look really promising. Numbers are high. We see a lot of, excitement in the community, but we often observe that in real life, things are a bit different. When we put these models into, practical scenarios, they often act funny. And we don't need sometimes adversarial examples to fool them. They do the job themselves. Okay, so I'm going to give you an example. So this is an image that I took from OpenAI's webpage, and I wanted a tool to generate a description for it. Now, I hope some of you might have noticed that PowerPoint now has this feature that if you click on this image and towards the left-hand side, it gives you an option that you can generate a description for it. So I took this example, and what it said, a person riding a horse. Very generic, very safe. So, acceptable if for a blind person, yes, a person is riding a horse. But depends on a person that, is requiring the output. I nudged it a little bit more. I gave it something interesting. And what does it say? Two people with a dog. I didn't need any adversarial attack for that. And this is supposed to be a very good, model running behind. But we can say that at least we do have a technology that can generate somehow generic captions for concepts that are common. And that's great. I think with time we would see a lot of progress. And recently, Microsoft also released an app that can do a lot more, and it's targeted for visually impaired, and it can actually, describe images in different languages. It can recognize friends and describe their, emotions, and also it can identify currency bills, colors, and whatnot. Now, we have seen that the recent models can somehow interpret a visual data. Well, whether it can imagine something out of a textual prompt. So if you read these prompts, I'm sure you can imagine, you can form some sort of a visual imagery in your brains, and it's unique to you. And now let's see if AI can imagine this as well. Now, if I've asked you to draw your imagination on a piece of paper, it might have taken you more than a minute or so, but this technology did it in few seconds. Mind the three fingers, Mona Lisa. It's like it does imagine a lot of things. It doesn't know, that it has to use common sense in a few things. So it's more of an artist compared to what I'm looking for. So yes, it can imagine things. And text-to-image synthesis is a very recent field. So the first model that was that came into being was or proposed was in 2016, where the authors they used a GAN to generate simple, very relatively small in size images for a restricted data set. Fast forward 7 to 8 years, we see OpenAI's DALL-E. So OpenAI has not only, caused some buzz because of ChatGPT, but DALL-E is a very famous multi-model thing as well. So where did the name came from? So it was inspired by Salvador Dali and Wall-E. What does it do? So it's capable of synthesizing images from the textual description of visual concepts or objects that you need. And next year we have DALL-E 2, which is an even more advanced version. And the good thing is, compared to DALL-E, DALL-E 2 has half the number of parameters. So it's not like ChatGPT that is just growing, in terms of parameters. So they have somehow worked on the efficiency as well. And what is it capable of? So given an image, it can, expand the canvas, which is very exciting, depending on the textual prompts that you give it. And somehow, this image, the background, it has decided that the house is quite messy. You'll see the output, but a lot depends on what you require out of it. It can also do in painting. So what you can do is you can remove the parts of the image and ask it to replace it with something else, move things around, different styles. And it can also generate different versions of the same image, which is quite interesting. Now let's have a bird's eye view of what's working behind it. So again, we will see some sort of representations or encodings. So what happens is that it takes a textual prompt, and there is a text encoder, which is of course a transformer. It converts it into an embedding, a meaningful representation, and which is a text embedding. And that text embedding is then transformed into an image embedding, and then a decoder uses that embedding to make an image. So we do have a lot of things happening in between. There is a model that is prior and a decoder. They are again transformers. They are meant for they have specific purpose, but I'm not going to touch any technical details. What is interesting is these text embeddings and image embeddings, because they play a very significant role in how you're able to transform or translate from one modality to another. Now, these embeddings, DALL-E, it actually uses a model to extract these embeddings. And what that model is, that does is that it learns the relationship between visual concepts and textual data. And so given an image and some sort of description about it, it tries to minimize the cosine distance between the similar concepts. And again, it maximizes the distance between dissimilar concepts. And in doing so, it kind of learns the relationship between visual and textual concepts, which turns out to be very useful for such kind of models. Okay, now, so applications, I don't need to, it can be a lot of areas that can benefit from such type of technology. We're already seeing people, saving time by using visual imaginations of these models to create websites or design entertainment material, and it's going to get better with time. Yet again, we know that there are limitations. This model, again, like ChatGPT, it does have that inherent bias because the data on which it was trained on, it was just, taken from web. So it does have those biases. And it's incoherent when it's, it generates incoherent text. So it's not good at imagining text, makes, lots of mistakes. Also, it's not good at associating attributes with the objects. For example, if you ask it to imagine a purple box over a red box, it would really confuse and, it won't know which box is red and purple. So it would give you a lot of incorrect options as well. There is, of course, text to image misalignment, where you see that the text and image, they kind of have a similarity, but when you're really going for accurate matching or correspondence, you would see a disparity. So the elephant is actually not eating pasta, but it's eating something else. So actually it's incorrect, but because it has come up with an image, we find it interesting. And that's why we have to be careful where we use this technology. As an artist, it's going to revolutionize how we create content. But as a scientist, or as an educator, you have to be very careful on what you use. For example, I work with medical images, and I wanted to know how a calcified abdominal aorta looked like. And it's a horrendous image that it came with. Like, it just hallucinated something, which is not, what we want to use. But if I'm going for creativity, it's good enough. So like any domain, it needs effective metrics to really ensure that what we want is what we're getting, not just the numbers. We have to be, we have to take human assessment into consideration, because unlike text to text, we are moving from image to text, and I think it's a huge jump. We are moving from one modality to another. So towards the end, I wanted to just, close the loop. I wanted to go from image to text and text to image because this is what I wanted to talk about. So I thought, let's start with an image and ask this PowerPoint tool to translate it. If it's clearly visible, these guys are holding wombats, okay? So what does the model say? A group of people holding animals, quite generic and safe. Okay, I'm gonna, forgive you for stuffed animals. Stuffed animals do look like that. And then I took the same description and gave it to DALL-E. Wow. So it is, it generates or hallucinates people holding stuffed animals. But if you zoom in, you might get, some interesting observation. The people who are holding these animals, they have deformed, I don't know, limbs and eyes, and better not look at this picture before going to bed, okay? So yeah, with this, thank you so much for listening. I hope, you would try this at home. It's quite interesting, and wish you good luck for this. Yes.
You think probably easier if I use the. I think it's easier if you use my computer. Yeah. Because then we don't need to log into Teams.
Okay. Just grabbing your slides.
Thank you. Oh, good morning, everyone.
Morning.
So I'm a bit, I was running across campus to try to get here on time.
You can talk.
Yep, so while
yeah.
that's getting started. So what I wanted to talk to you about was what I've been working on over the past couple weeks, and that was an attempt when this all kind of hit the news in December, January. I thought, okay, as an academic, could I use this to replace my tutors? Not said it in a nasty way, but the amount of time that would require answering usually the same permutations of the same questions year on year on year. Is this a vehicle that I can offload that and free up the tutors to actually do unique things with each student? Of course, I didn't know Python. And well, I should admit that. I didn't know Python to start with and had no idea how these models work. So picking up on the last presentation, this has taken me about 2 weeks to learn from start to finish. It's really not hard for academics to understand maths and linear algebra. And what I wanted to show you is the outcome, basically, of that exercise. Sure. Do you have any news?
No, it's somehow lost your email. That doesn't make sense.
We don't have anyone from IT.
Ah,
Here. Yeah.
Journalist team.
But some teams, it's conducted in those teams.
I could just put that laptop right there facing the screen so people could watch it. Would that work?
yeah, if you just log into Teams and join this, and I think that would be good.
Yeah.
Put your computer here onto the screen and they can just use it as a projector. Use your screen,
Yeah.
use your camera.
Okay. That will be right.
You sure? Because it's working right here. So if it's just as if this is like a mini Tim sitting in the front row.
No, we lost your screen. Okay, so we have to really face.
It's only
Hey,
going to be
this-
10 minutes. It's a very quick overview. I'm not a programmer. I'm not a computer scientist.
No,
I can't tell you anything
it doesn't
new.
work.
Just the academic experience. You have to log into the screen.
Yeah, yeah. Sorry about that. So if you go to browser.
Oh. This computer still works. Okay.
That's all good now.
Cool. So what I did, so I actually found on YouTube there's some really good tutorials to start learning what are these embeddings that we were just hearing about. And the real power of ChatGPT, and I wanted to put up in the title, not.com, because literally, except for this, every seminar I've seen in the past 2 weeks goes to the website and talks about what students can do on the website. And it became very clear very quickly that that is a reductionist mentality that absolutely misses the power of this tool. So I figured out you can basically write Python scripts that will talk to OpenAI, and you can import OpenAI into Python, so you can retrieve and send these embeddings for any content you want anywhere. And I thought, oh, cool. Okay, so then I found a YouTube tutorial that was talking about how to do this with things like memory involved. I don't know if anyone follows David Shapiro, but I kind of hooked onto his channel and then started looking at his repositories. So in the first instance, I built 2 bots that I'm rolling out this semester for my undergraduate chemical thermodynamics class. The first looks at any query that's coming in from the user and says, okay, I only care about answering 3 types of queries. One is general chat, talk about rugby, talk about cricket, I don't care. One is policy, maybe the students want to figure out, are they eligible for special consideration? And the third is the technical chat, the reason that we're actually there. So in a general discussion type, what it does in the standalone bot is difficult. It will remember and after every chat sequence, it looks through its memory of what happened recently to learn from it in summaries. So then when you ask it a new query, it delves into these summaries and says, have we talked about anything like this before? And what it's doing there, if you send it a query, it sends that to GPT. Oh. Okay. So we'll look through everything and talk about this, retrieve that, and add it into what was called a corpus as it constructs this response. Now, beyond that, I went through 227 UWA policies from our websites. Really good fun. And I fine-tuned it on all those policies. So the fine-tuning process for a non-computer scientist was super easy. The Python script says, take this document, cut it up into 500 character chunks. I send each chunk out to GPT to say, what is the And this is what I've called Terry. This is the thermodynamics. Terry response. So this is Terry's response. Now, in my mind, this would be a postgraduate level response to the question of understanding how entropy is embedded in molecular level. So that was the first bot, standalone persistent memory. It loads about a gigabyte and a half when you first open it, and it takes about 5 or 6 seconds to respond. That's useful for perhaps an offline application, but not for a class. So I wrote another bot that takes that and stripped away everything that was taking too long to respond. And the goal is that we're going to try to get this into my class team by Monday of next week. I appreciate the difficulty. But this thing can work in about 2 seconds to respond. And so it's working in the bot emulator. It should be compatible with Teams. We can try and do some checking. So when the user starts a query, the first thing it does is goes out to the ADA engine, which is the highest ranked embedding engine for giving good similarity. What type of question am I answering? General, administrative, technical? Policy libraries are still there. General is still here. What we do is in the team spot, we can't have a persistent memory that can get verified in. And for all technical queries, it will look to all of the core disciplines of what I'm looking at, chemical engineering, right? So in green, I've labeled those fundamentals. In yellow are the kind of core disciplinary topics, and in red are the meta topics. So we're going to pull multiple core disciplines to make an answer. It then looks through 2 textbooks in each library and finds what are the best similarity matches across all of these libraries. Ranks what are my top 3 disciplines out of the 12, and what's the proportion of each discipline of the top 3. So if I ask a pure thermo question, then I'm going to base all 3 corpus elements from thermo. But if I have an equal split from thermo, fluids, and heat mass transfer, it's going to pull 1 from each. So it brings all these corpus elements together, and the direction that it gives ChatGPT is you are only to construct a response based on the dot point information I've given. Here's what the student asked. Here are the dot point facts you base it on from these searches. These are coming from written textbooks. And you need to write a response that's intelligible to an undergraduate student, which it then does and pops back out to the user. So in my testing of it, then what I've seen is answers that at a technical level for undergraduates were somewhere in the high 90th percentile accuracy. Because I'm not using any of the intrinsic information that it was trained on to answer the question. I'm using my so this is the general structure of then what would constitute that corpus. The really interesting part that I took away from it is that half of it was understanding how the embeddings were created and retrieved. And the other half was structuring the prompt text file that you give it, so prompt engineering, to use the right words in English to force the engine to not embellish, to not hallucinate. So importantly, when we hear in some of the more like academic and policy seminars, well, it's only 80% accurate. Yeah, out of the box. Right? How many humans do you know out of the box that are 80% accurate? Right? We have to go through a lot of training. So in this context, what I can do is say, well, this is as accurate as the textbook materials I've used to build. And the only hallucination possibility of that is if I write the prompt in such a way that it's not, or that it gives it an opening to embellish or hallucinate. So then I thought, so we're going to try to do both of these bots this semester. But I wanted to run a few examples. So if I use like a 4th or 5th year student that's traditionally iterative, student asks a question about entropy, this can get pretty hard, right? So it's going to take a young PhD student 3 minutes to write a response that's somewhere in the realm of coherence. If I look at the compute time from OpenAI, it takes 3 seconds to construct that K response. So then I think, okay, well, how many questions do I get per semester? How many more questions will students ask if this is that accessible? And you can linearly project what's your enrollment in each class, and how much cost savings could you have diverting Q&A to a bot like this that's fine-tuned, thereby opening up tutors to do hands-on, practical experiential. And if you look at perhaps like the 500-person accounting unit run out of business, that's a cost savings that hits up in the tens of thousands, right? But don't know what it would be until we measure it, but it'll be somewhere in the order of magnitude. So I think that's everything. Yes, that's everything. Any questions?
That sounded normally interesting. We're definitely not trying to damper on anything. OpenAI is getting away with these sort of things by just treading on everyone's copyright and intellectual property and so on. I'm wondering, publishers know that we're feeding our own internal tools with digital copies of their textbook, which then, of course, students aren't blind. Does UWA become a target for them?
That's a great question. I have no idea what this is. What I can tell you is the way that it's constructed, like that kind of. So the what it does to get that's sufficiently compressed asks GPT summarize very low temperature, high temperature, summarize each in say less than 50. So what it's actually feeding into the actions is a summarized.
So that's analogous to you and I reading a textbook and having a few beers and then writing our own PowerPoint slides based upon half of what we've said.
Yeah.
And that's what we can get away with.
So in the realm of the publishers, is that a violation of copyright? I don't think so. Because if I ask a PhD student to do the same thing, it's a violation.
So one's paraphrasing and the other one's sort of summarizing without actually through that consciously text or something.
I don't disagree that context of publishers survive in the new world. Anyway, the part that really blew me away was looking at these kinds of numbers, whether or not I'm off by a factor. Right? No organization that's concerned about money as much as any university has per year. And look at between 10 and 100. If we do, we lose the right to complain about money. So it's an opportunity, I think, for us not to go beyond feelings with things like this and actually bottom line and for business. So one kind of final idea I wanted to end is if this is successful enough and if we don't have huge problems doing this in maps, it would be nothing from desktop apps and drop your file. It's going to go away, strip it, build the indices, bring your libraries back, and it's plug and play for a backlog of files.
Perhaps students could drop their own copies of the digital textbook in there.
Yeah, that would be another.
Or their
Nice. Not very nice. Yeah. This reminds me a bit of those little things of mine. You go on the website and you say you got them up like better than that. I like it. Perhaps you can make money and sell it to customer.
Well, in my mind, the amount of time, especially with the introduction to 2020, the amount of time last year that I spent on answering unveiled. And it's not our fault, right? The students like this. They like the asynchronous chat. They like so it's a way that we can survive in that world and still have time to do research. Currently 63 enrolled, estimating about 75. Actually, that's, yeah. So if this works, because we're doing this as a trial, right? Because we're doing it with live humans that actually need to learn. So it's a trial right now in which I place no promise in what it can do. If it works, what I'd like to do is a formal test next semester with different units. See if we can get an ethics approval to then look at comparative outcomes with and without a tool like this, offered from a non-technical perspective. So then actually start arguing that.
What sort of, you mentioned that, so it's, you're not going to save all of the unit budget because the tutors are going to be doing something, sorry, the facilitators are going to be doing something more valuable. What sort of things do you think that would be? And how do you think, and sorry, second question, how do you think students might react to this? Because they're pretty toey about recorded lectures. You know, oh, you're using last year's recorded lecture, I paid for this.
So I think that's I don't know. I don't have any idea how they will react. Folks that talk to that have kids that are this age, which I do, have mentioned that the younger generations don't have a problem parenting fully with NPCs and for that. Right? The type of they don't mind the idea that there's not another human behind this, and somehow conceptually or cognitively that doesn't throw a switch for them. It would for me. So if that holds true, then hopefully we don't get a pushback. But in terms of what it would free up facilitators to do, hands-on for time doing. and less time writing responses for students that are just asking.
Yeah.
You tried to, sorry, can I ask a question? Yeah. Have you tried to ask it to explain it in a more layman terms?
Yes.
You did?
I even, so my favorite question I threw at
Yeah.
it, because I said, entropy is giving me, I'm giving me generalized social anxiety. I think that makes me eligible for spectrum. What do I do? Right? And so the thing, looked at our chat history and said, oh yeah, I can see that we've been talking about this a lot, was this first part of the response. It turns out in statistical mechanics, a number of famous professors have committed suicide in studying it. So I appreciate that this is a significant problem. However, you are always eligible for special consideration under policy. You must bring a medical certificate for demonstrating otherwise extenuating circumstances. So it was able to take that and parse the response across all three domains.
So it's actually cross the policy with the content.
Yeah, for the standalone bot that has that you can load 4 gigabytes of, it will pull all three domains, and then in the technical domain, pull sub-technical domain.
Are you happy to share the code with us?
Yeah. Please don't judge. I tried to comment most slides. I've not put it for a while. Please don't judge. But no, it's on GitHub, so I'll say it.
Yeah, and if you manage to get any success on integrating with the Teams bot, do keep us posted.
I got a positive email this morning.
Oh,
I
excellent.
think they're trying to make sure it only locks to this team. It doesn't roll out to all of university, which is the current concern.
Okay.
Cool. Well, thank you for the opportunity. Yeah.
I think you'll. Thanks so much. Yeah.
Tables, like material and energy balances. Yeah. But the deal with those quite well.
Absolutely. And the way I talk that, so in the each of these has text prompts. So it pulls elements into the text prompt, into the summary or what. So in that layer of text prompt of summarizing, because if there are summarized. So it's really at the level of answer. That's from right.
So if the table or a figure had a very good caption.
Yeah, if it's as long as it's written text, it doesn't. But I told it I had to really play with the language correctly, but basically stop repeating numbers and equations. Can't put those in text. Yeah,
questions and answers and problems and you ask.
Like one of my calculations. Anything but a calculation now. Absolutely. And that was the goal, right? Was to get it so if I can get this to the point that it can take my exam and do well.
Yeah, exactly.
And I give this to every student. What am I going to do with my exam? It's going to get really fun, right? Now it's going to play, and I'm going to have a really fun exam that's going to challenge. That was my image. Thank you for the opportunity.
That's great. Thank you so much for taking the time. Right. So there's still some food left over. If people wants to stay behind chat, feel free to do that. Yeah, there's no more tea or coffee. We didn't have time to do that. Thank you so much for taking time. Yeah, it's a lot of hours and efforts, and especially thanks to all the presenters. Thanks. Very good. Yeah. Thank you. Yeah. Thanks everyone. Have a nice weekend.